In 2024, a group of physicists working at the University of Toronto carried out an unusual experiment that quietly challenged one of the oldest assumptions in modern physics. Deep inside a dimly lit laboratory, the results they observed began to unsettle not only the scientific community, but humanity's entire understanding of time itself. Because for a brief moment, researchers detected measurable signs suggesting that time may not flow as rigidly forward as we have always believed. This was not science fiction, a simulation theory, or a philosophical thought experiment written only on paper. It was a real physical experiment conducted with real instruments, producing observable and measurable data. And for a fleeting instant, it felt as though one of the hidden mechanisms behind reality had stumbled, like the hands of a clock hesitating before slowly turning backward. The event raised a far more unsettling question. What if time is not what we think it is? Perhaps the line between past and future is nothing more than a fragile illusion created by the human mind. That small anomaly, recorded in the silence of the laboratory, became one of the first tiny fractures in the smooth fabric of reality itself. And if you enjoy calm nighttime journeys into the unknown corners of the universe, journeys that slowly pull the mind into deeper reflection, then this story may be exactly what you are looking for. So dim the lights, relax, and let us gently drift into the mystery of what time might truly be. Now allow your mind to slowly drift and follow that faint beam of light moving quietly through the darkness, because tonight's journey will take us somewhere most documentaries never dare to go. We are not traveling to the frozen edges of distant galaxies, nor descending into the unreachable depths of Earth's oceans. Instead, we are moving toward one of the most unsettling questions modern physics has ever asked. What if time is not what humanity believes it to be? What if the boundary between past and future is only a fragile perception created by the mind itself? Near the end of 2023, inside a quiet underground laboratory in Canada, physicist Ebrahim Karimi and doctoral researcher Daniela Angulo found themselves standing at the center of that very question. The experimental system they had spent 3 years building looked almost otherworldly beneath the dim laboratory lights. Tangled cables, metallic instruments, and laser systems calibrated with extraordinary precision filled the room with an eerie stillness. Yet despite all of that complexity, the purpose of the experiment was surprisingly simple. The researchers were sending individual particles of light, known as photons, through a dense cloud of ultra-cooled rubidium atoms, carefully observing how reality itself behaved in that precise moment. And before long, a small and unexpected result emerging from the silence of that laboratory would begin to challenge everything we thought we understood about time itself. The interaction between particles of light and atoms is considered one of the oldest and most understood processes in quantum physics. When a photon enters a dense cloud of atoms, it can briefly be absorbed by one of them. In that instant, the atom jumps into a higher energy state known by physicists as an excited state. Then, after an unimaginably short delay, the atom releases that stored energy and calmly returns to its normal condition. Under ordinary circumstances, the process is perfectly predictable, because like every physical event in the universe, it requires a measurable amount of time. Even if the duration is incredibly small, time is still expected to move forward. The goal of the research team was to measure exactly how long the atoms remained in this excited state with extraordinary precision. To do this, they introduced a second beam of light into the system. This additional probe beam acted like an invisible stopwatch, allowing the researchers to observe how long the photons spent inside the atomic cloud. At first, the incoming data appeared completely normal, but only moments later the silence inside the laboratory turned into confusion. There was no equipment failure, no damaged sensors, and no obvious calibration problem. Every instrument was functioning exactly as intended. The problem was the result itself. According to the measurements, the atoms had spent a negative amount of time in their excited state, less than 0. It was as if the particles of light had somehow exited the atomic cloud before fully entering it. And if you had built an invisible quantum clock capable of measuring that microscopic interaction, you would have watched its hands briefly move backward. In that moment, everyone inside the laboratory was forced to confront the same unsettling possibility. Perhaps time was never as one-directional as we believed. When Ibrahim Karimi and his team revealed the extraordinary results of their experiment to the scientific world, the first reaction was not excitement, but silence. Because what appeared on the screen was more than an unusual measurement. To many physicists, it looked like one of the first tangible signs that time itself might behave in ways completely opposed to human intuition at the quantum level. Soon, that silence turned into disbelief and fascination. Some researchers argued that the effect was simply a strange consequence of quantum measurement techniques, while others considered a far more unsettling possibility. Perhaps, deep beneath the surface of reality, time was not moving in the smooth, straight line we had always imagined. Yet the scientists behind the experiment were extremely careful about one thing. This was not time travel in the way most people understand it. No information had been sent into the past. No particle had moved faster than light, and the laws of physics had not collapsed. But even so, the implications remain deeply disturbing, because at the smallest scales of nature, time itself might not behave like the rigid one-directional flow we experience in everyday life. The human mind has always imagined time as a river moving endlessly forward. The past disappears behind us, the future slowly approaches, and nothing ever turns back. But inside the silent darkness of the quantum world, reality no longer seemed fully committed to that rule. And perhaps that was the most unsettling thought of all. The universe may not operate the way we feel it does. The impossible value measured inside the laboratory was, strangely enough, not violating any known laws of physics. The elegant universe described by Albert Einstein still remained intact. The equations still worked, and reality itself appeared stable on the surface. Yet somewhere deep within the quantum world, something profoundly unsettling had taken place. In the large-scale world we experience every day, causes always come before effects. A door opens, and then someone walks through it. A star explodes, and only afterward does its light reach us. Time moves forward, and reality faithfully follows that order. But at the microscopic scale ruled by atoms and particles, nature begins to behave as though it is operating under entirely different rules. To better understand this strange idea, imagine a simple but deeply disturbing scene. You are standing at the entrance of a long, dark tunnel. Hundreds of cars are entering one after another. While you carefully record the exact moment each vehicle crosses the entrance using an extremely precise stopwatch. Then you move to the opposite side of the tunnel and begin recording the exit times as the cars emerge. At first, everything seems perfectly normal, but suddenly, something impossible appears in your data. Some vehicles seem to leave the tunnel before their recorded entry times, as if the effect had occurred before the cause itself. Of course, in ordinary life, such a thing would be absurd. Yet in the strange mathematics of quantum physics, behaviors very similar to this had been predicted for decades. For many years, physicists assumed these effects were only theoretical oddities hidden inside equations. But now, in the silence of a dark laboratory, that impossible behavior was beginning to look frighteningly real. In the world of physics, this strange phenomenon is known as negative group delay. For decades, most scientists treated it as nothing more than a mathematical curiosity. It was seen as an abstract effect emerging from the strange equations of wave mechanics, something that existed only inside calculations without carrying any true physical meaning in the real world. To many researchers, it was simply a harmless anomaly hidden inside the mathematics, an illusion created by nature itself. But the team at the University of Toronto chose a far more daring approach. They did not limit themselves to measuring when the particles of light appeared outside the system. They also attempted to observe what was happening deep inside the atomic cloud itself. The simplest way to imagine this is to think about the traces left behind by cars moving through a tunnel. If the vehicles truly pass through the tunnel, then something inside the tunnel should reveal evidence of their presence. In the quantum world, that evidence was the amount of time the atoms remained in their excited energy state. When the researchers measured that duration directly, the result was deeply unsettling. Once again, the numbers came back negative. It was as though the particles had somehow left their fingerprints on the system before fully interacting with it. And suddenly, not only the external observations, but the internal physical processes themselves were telling the same impossible story. That was the moment physicists became truly disturbed, because negative group delay was no longer just an abstract equation or a mathematical trick. For the first time, it appeared to represent something physically measurable inside reality itself. The tiny negative sign appearing on the screen was no longer just a symbol. It looked like physical evidence of a strange hidden behavior buried deep within the fabric of existence. And according to Josiah Sinclair, one of the theorists behind the study, the implications might be far greater than anyone expected. The idea of a negative time delay sounds deeply contradictory at first, almost impossible for the human mind to accept. We naturally experience time as something that moves only forward, carrying every moment from the past into the future, without ever turning back. Yet if you could build a perfect quantum clock capable of measuring how long atoms remain in their excited state, there are conditions under which the hands of that clock would appear to move backward instead of forward. And that is precisely why the experiment ignited such intense debate across the scientific world. One of the most well-known theoretical physicists, Sabine Hossenfelder, strongly criticized the way these results were being presented in explanations watched by millions of people. According to her, the measured negative duration did not mean that time itself was literally reversing. Instead, she argued that the effect was simply an unusual consequence of how photons behave in shift phase while traveling through certain materials. In her view, the conclusions surrounding the experiment were being exaggerated far beyond what the physics actually implied. But the research team behind the experiment responded with equal confidence. They explained that the measurements were consistently reproducible. The instruments were functioning with extraordinary precision, and that years had been spent perfecting the system itself. Whatever was happening inside that ultra-cooled cloud of rubidium atoms was undeniably real, and the result appearing on their screens left very little room for doubt. The measured value was below zero. In ordinary life, we think of time as an arrow moving in only one direction. We are born, we grow older, and every second pushes us further into the future. But the strange data emerging from the depths of the quantum world suggests that time may not be as absolute as we once believed. Inside the invisible realm ruled by atoms and particles of light, reality no longer seems fully committed to the orderly flow we experience every day. The smooth line connecting past, present, and future begins to fracture at the quantum scale. And perhaps the strangest part of all is this: the mathematics of quantum mechanics has been quietly whispering this possibility to us for nearly a century. Only now are we finally beginning to see those impossible numbers appear directly on the screens of our machines. And it is precisely here that the question capable of quietly reshaping our entire understanding of reality begins to emerge. If time can behave so strangely at the quantum level, if under certain conditions it can appear to move backward, and if the boundary between cause and effect can begin to blur, then what exactly is time? Is it truly the one directional current humanity has been trapped inside since the beginning of existence, carrying us endlessly toward an unavoidable end? Or is it simply a useful story created by the human mind to make the chaos of the universe easier to understand? Perhaps nature is far more flexible, far stranger, and far less bound by rigid rules than we ever imagined. Perhaps the direction of time is not as absolute as it feels. What makes this even more fascinating is that the idea of time being an illusion did not begin inside modern laboratories. Long before humanity understood atoms, photons, or quantum mechanics, ancient cultures across the world were already telling stories that touched the same unsettling possibility. In India, Japan, Ireland, and throughout the ancient Middle East, stories were passed down about travelers who entered strange realms where time moved differently. In many of these legends, people would spend what felt like only a few hours in another world, only to return and discover that decades or even centuries had passed in their absence. The people they once knew were gone. Entire cities had changed, and the world they remembered no longer existed. Of course, those ancient storytellers knew nothing about relativity or modern physics. Yet their descriptions of time flowing differently in distant places carried a strangely unsettling resemblance to ideas that science itself would only begin to formalize thousands of years later. It was almost as if humanity had always sensed, somewhere deep beneath consciousness, that time was never as simple as it appeared to be. Later in our journey, we will return to those ancient stories of mysterious travelers and legendary realms where time seemed to flow differently. But before we reach those distant myths, we need to understand something far closer to our everyday lives. You do not need a laboratory, a particle detector, or pages of complex equations to witness time bending. Because even now, while you are listening to these words, the invisible fabric of the universe is quietly moving around you at different rhythms. And whether we realize it or not, every human being is already traveling through time. We tend to believe that time flows equally for everyone, carrying all of us forward at the same steady pace from the moment we are born. But reality is far stranger than that. People living in different places on Earth do not experience time in exactly the same way. Someone standing at sea level and someone high above on a mountain peak are not moving through time at an identical rate. A traveler flying through the sky and a person standing motionless on the ground age at subtly different speeds. And today, this is no longer philosophy or speculation. It is a measurable and mathematically proven fact of nature. As we lift our eyes away from the flexible and unsettling depths of the quantum world and turn toward the larger structures of the cosmos, we encounter the mind that permanently transformed humanity's understanding of reality itself. In the early years of the 20th century, a young patent clerk, living quietly in Switzerland, began developing an idea that would completely shatter our assumptions about time. In 1905, in the city of Bern, the 26-year-old Albert Einstein published a paper that would forever change the way humanity understood time. And from that moment onward, time was no longer just the simple ticking of a clock. At the time, Albert Einstein was not a famous scientist. He was not teaching at prestigious universities, leading powerful laboratories, or surrounded by teams of researchers. After graduating, he struggled to secure a position in academia and eventually found work in a small government patent office in Switzerland, where he spent his days reviewing applications for electromagnetic devices. From the outside, his life appeared completely ordinary. Yet inside that quiet office, sitting alone at a small desk, Einstein was developing ideas that would permanently transform humanity's understanding of reality itself. In 1905, he published a paper titled On the Electrodynamics of Moving Bodies, a work that would later become known across the world as the theory of special relativity. And at the center of that theory was an idea so strange that it initially sounded almost absurd. According to Einstein, time was not absolute. Before him, most scientists believed time flowed identically everywhere in the universe. A second was assumed to be the same for every observer, no matter where they were or how they moved. Isaac Newton had placed this assumption at the very foundation of classical physics. In Newton's universe, time moved forward steadily and independently, untouched by the outside world, like an invisible cosmic clock, ticking evenly throughout existence itself. But Einstein revealed that this picture was incomplete. Time did not move equally for everyone. The faster an object traveled, the more slowly time passed for it relative to someone standing still. And this was not poetry, metaphor, or a trick of human perception. It became one of the most repeatedly tested and confirmed truths in all of modern science. Yet Einstein did not stop there. 10 years later, in 1915, he introduced the theory of general relativity, revealing that not only speed, but gravity itself could bend time. Suddenly, the universe was no longer an empty stage where events simply unfolded. space and time became part of a flexible fabric capable of stretching, warping, and curving under the influence of massive objects. The closer you moved toward a planet, a star, or a black hole, the more slowly time would pass for you. Because gravity was not merely bending space, it was bending time along with it. And from Einstein's equations emerged one of the most unsettling ideas in modern physics. If time flows differently in different parts of the universe, then perhaps the separation between past, present, and future is not as absolute as we once believed. Perhaps the human mind is interpreting reality incorrectly. Perhaps the past never truly disappears, and the future is not an empty void waiting to be created. Perhaps every moment continues to exist simultaneously within the hidden structure of the universe itself. It was almost as if the entire history of the universe already existed at once, like the pages of a vast completed book waiting silently to be read. The past, the present, and the future were not separate moments disconnected from one another, but different sections of a single structure. Human beings were merely observers moving through those pages one by one, believing each moment was being created as it happened, while perhaps we were only experiencing a reality that already existed in full. Albert Einstein expressed this unsettling idea very clearly near the end of his life. In 1955, after the death of his close friend, Michel Besso, Einstein wrote a deeply revealing letter to Besso's family. In that letter, he explained that his old friend had merely departed from this strange world a little earlier than he had, but that from the perspective of physics, this difference held no real meaning. He then wrote one of the most haunting sentences associated with modern science. For those who truly believe in physics, the distinction between past, present, and future is only a stubborn illusion. These were not the poetic reflections of a novelist or mystic. They were the calm conclusions of one of the greatest minds humanity has ever produced in its attempt to understand the hidden nature of time itself. To Einstein, the idea that time flowed smoothly in one direction was not an ultimate truth, but a limited interpretation created by human consciousness. And perhaps the most unsettling part was this: these ideas did not remain trapped inside philosophy or theoretical papers. Before long, they began to be tested inside laboratories around the world. Humanity started directly measuring the fact that time could bend, slow down, and flow at different rates under different conditions. And the results suggested that Einstein's terrifying intuition about reality may have been far more accurate than anyone once believed. Now we move beyond the abstract world of theory and into the physical experiments that proved time itself can bend. What made Albert Einstein's ideas so extraordinary was the fact that they were not merely elegant mathematical predictions written on paper. Over the decades, relativity was tested again and again, and each time the universe behaved exactly as Einstein said it would. One of the most remarkable demonstrations took place in 1971, when physicists Joseph Hafele and Richard Keating carried out an experiment that would directly measure the flexibility of time itself. They placed highly precise cesium atomic clocks aboard commercial passenger airplanes. Some of the clocks traveled eastward around the Earth, while others flew westward. Identical atomic clocks remained stationary on the ground for comparison. The setup sounded surprisingly simple, yet the implications were profound. Once the aircraft completed their journeys and returned, the scientists compared the clocks. The results matched Einstein's predictions with astonishing precision. The clocks no longer agreed with one another. The clocks that traveled east had fallen slightly behind the clocks on Earth, while the westbound clocks had moved slightly ahead. Time itself had flowed at different rates depending on motion and gravitational conditions. For the first time, humanity had directly measured the fact that time is not universal. But the story did not end there. As technology advanced, the evidence for time's strange flexibility became even more precise. In fact, one of the clearest examples now exists quietly inside the smartphones people carry every day. Modern GPS technology depends entirely on Einstein's theories. The satellites orbiting Earth travel at nearly 14,000 kilometers per hour, while floating thousands of kilometers above the planet's surface. At those altitudes, gravity is weaker than it is on Earth, while the satellites themselves are moving at extremely high speeds. And this is where both special and general relativity begin operating simultaneously. Their immense speed causes onboard clocks to run slightly slower, while the weaker gravitational field causes them to run faster. These effects do not perfectly cancel each other out. As a result, the clocks aboard GPS satellites advance roughly 38 microseconds faster every single day compared to clocks on Earth. And if engineers failed to constantly correct this difference, the navigation systems in our phones would drift by kilometers within days. So even without realizing it, modern humanity already relies on technology that quietly confirms one of the strangest truths in physics. Time is not fixed, it bends. 38 microseconds may seem completely meaningless to the human mind. It is a duration so tiny that no person could ever consciously notice it. Yet within the mathematical precision of the universe, even a difference this small creates enormous consequences. If engineers on Earth fail to correct the time drift inside GPS satellites every single day, the entire system would eventually collapse. Without those corrections, the location displayed on your phone would begin drifting by kilometers each day. Navigation systems would rapidly become unreliable, and before long your device could place you in a completely different city. So every time you open a map application to find an address or navigate through an unfamiliar place, you are unknowingly relying on Albert Einstein's theories about the flexibility of time itself. For the satellites orbiting high above Earth, time genuinely flows at a different rate than it does for you on the ground. And as technology has advanced, humanity's ability to measure these differences has reached almost unimaginable levels of precision. In 2024, inside a laboratory in Boulder, physicist Jun Ye and his team used one of the most precise instruments ever created, known as an optical lattice clock, to measure gravitational time dilation across distances smaller than a single millimeter. They discovered that even across a gap thinner than a human hair, time itself was flowing at measurably different rates. The universe was revealing that time is not universal or fixed. It is a flexible physical structure that changes depending on speed, gravity, and location. But this is where the story becomes truly unsettling, because the flexibility of time does not affect only machines, satellites, or laboratory instruments. It affects living organisms as well. Human biology, our cells, our heartbeat, and even the process of aging are all tied to these invisible laws of the universe. One of the clearest demonstrations came from the famous observation involving NASA astronaut Scott Kelly and his identical twin brother Mark Kelly. Scott Kelly spent nearly a full year aboard the International Space Station, while his brother remained on Earth. As Scott orbited the planet at nearly 28,000 kilometers per hour, Mark continued living under the stronger gravitational pull of Earth. When the mission ended and Scott finally returned home, scientists compared the biological measurements of the two brothers. The results became a living confirmation of the predictions Einstein had written decades earlier, using nothing more than paper, ink, and thought experiments. Scott Kelly had aged ever so slightly more slowly than his brother, and for the first time humanity witnessed that time does not merely alter clocks, it can alter the human body itself. When Scott Kelly returned to Earth, he had aged ever so slightly less than his twin brother Mark Kelly, who had remained on the planet. The difference was only a few milliseconds, far too small for any human being to notice directly. But the importance was never the size of the difference. The importance was the fact that the difference existed at all. That tiny measurement proved that the laws governing time were capable of affecting the human body itself. Mark Kelly later joked about the situation by saying that he used to be only a few minutes older than his brother, but was now a few minutes and a few milliseconds older instead. Yet behind that small joke was an astonishing physical reality. Scott Kelly had traveled into space, moved around Earth at extraordinary speeds, and returned slightly younger than he would have been had he never left the ground. This was not a psychological feeling or a poetic metaphor. The atoms inside his body had genuinely experienced less time. His cells had aged more slowly. His biological processes had unfolded at a subtly different rate. In a very real sense, he had moved through the fourth dimension differently than his brother. And one of the most striking examples in human history came from Sergei Krikalev. After spending enormous amounts of time in orbit throughout his career, Krikalev returned to Earth roughly 20 milliseconds younger than he would otherwise have been. Technically speaking, he became one of humanity's first verified time travelers. Now imagine expanding these effects further in your mind. If humanity someday builds a spacecraft capable of traveling near the speed of light, the distortion of time would become dramatically more extreme. A journey lasting only a few years for the passengers could correspond to decades passing on Earth. You could leave your planet while still young, travel among the stars for what feels like a relatively short time, and return to find that everyone you once knew had grown old. Entire cities had changed, and the world you remembered no longer existed. And the unsettling part is this: none of this belongs only to science fiction. These are direct consequences of the equations developed by Albert Einstein and repeatedly confirmed through decades of experimentation. Forward time travel is no longer theoretical speculation. It is a measurable law of nature. Even now, while you are listening to these words, you are aging at a slightly different rate than someone standing at a different altitude or moving at a different speed somewhere else on Earth. The differences are far too small to feel in everyday life, but they are always there, quietly accumulating within the hidden mathematics of the universe. In the end, traveling into the future is not fantasy. According to modern physics, it is already happening. Most physicists agree that time can bend forward. Traveling into the future is no longer just a philosophical thought experiment, but a direct consequence of modern physics itself. Yet the moment we begin asking whether the arrow of time can reverse, whether the locked doors of the past can somehow be reopened, reality becomes far darker and infinitely more complicated. Because traveling backward through time does not merely challenge physics, it threatens the very foundation of logic itself. For most of the 20th century, scientists believed that reversing the flow of time was impossible. Albert Einstein's equations allowed time to stretch, slow down, and propel travelers into the future. But those same equations appeared to preserve causality. Causes had to come before effects. The past could not be rewritten. And so for decades, backward time travel was treated not as serious science, but as material for science fiction novels and fantasy stories. Then, in the middle of the 1980s, an unexpected phone call quietly changed everything. That single conversation would eventually open the door to one of the most dangerous ideas in the history of physics. Around that time, the famous astronomer and science communicator Carl Sagan was writing a novel. Even this was unusual. Sagan was known not for fiction, but for his contributions to science, and for the extraordinary way he explained the universe to millions of people. He was the legendary host of Cosmos, a respected professor at Cornell University, and a scientific advisor connected to major NASA missions. By that point, he had become one of the most recognized scientific voices in America. But this time, he wanted to tell a different kind of story. His novel followed a scientist attempting to make contact with an alien civilization after receiving a mysterious signal from deep space. The problem was distance. The destination star in the story, Vega, was located roughly 26 light years away from Earth. Even using humanity's fastest spacecraft, such a journey would require hundreds of thousands of years. Sagan needed a scientifically believable way for his main character to travel there and return within a human lifetime. At first, he considered using a black hole. For most science fiction writers, that explanation would have been more than enough. But Carl Sagan was not willing to bend the laws of physics simply to make his story work. He wanted the science behind the journey to remain completely consistent with reality itself. And so he decided to call someone he trusted deeply, the physicist Kip Thorne. That conversation would soon lead to an idea capable of permanently changing humanity's understanding of time. At the time, Kip Thorne was a respected theoretical physicist working at the California Institute of Technology. He was already considered one of the world's leading experts on general relativity, black holes, and the geometry of space-time itself. Years later, his work on gravitational waves would help earn him the Nobel Prize in Physics. But on that ordinary day in 1985, he was simply a calm professor answering a ringing telephone in his office. On the other end of the line was Carl Sagan. The question Sagan asked sounded almost like pure science fiction. Was there any scientifically plausible way to travel enormous cosmic distances without breaking the laws of physics or exceeding the speed of light? Kip Thorne treated the question with surprising seriousness, because beneath the fictional story lay a much deeper issue. Did Einstein's theory of general relativity actually allow such a thing to exist? For days, Thorne studied the mathematics carefully. and the solution he eventually reached would do far more than solve a problem inside a novel. That harmless thought experiment revived one of the strangest forgotten ideas in theoretical physics: wormholes. The concept itself was not entirely new. Its origins traced back to a 1935 paper written by Albert Einstein and Nathan Rosen. In that paper, the two physicists mathematically described hypothetical tunnels capable of connecting distant regions of space-time. These structures, later known as Einstein-Rosen bridges, acted like hidden shortcuts woven directly into the fabric of the universe. In theory, a traveler entering one side of such a tunnel could cross distances that would normally require millions of years in only seconds. It was almost like stepping through a doorway in a dark room and emerging instantly on another world far across the cosmos. The mathematics clearly suggested that space itself could bend in this way. But there was one overwhelming problem. Every wormhole model studied by physicists appeared catastrophically unstable. Nature seemed willing to allow these tunnels to briefly exist, yet completely unwilling to let anything safely pass through them. The moment a human being, spacecraft, or even a tiny particle approached the entrance, the wormhole would collapse violently in on itself. The passage would seal shut, crushing and destroying anything attempting to enter. So while wormholes appeared beautiful inside the equations, in physical reality, they behaved more like deadly traps than usable gateways through space-time. The flexible fabric of space-time behaved like a stretched elastic sheet, desperately trying to snap back into its original shape. Even if a wormhole could briefly form, it would collapse almost instantly under its own gravitational pressure. The collapse happened so violently and so quickly that not even light would have enough time to safely cross to the other side. But Kip Thorne decided to confront this seemingly impossible problem directly. If mathematics allowed wormholes to exist, then perhaps there was also a way to keep them open. Together with his students, Thorne spent months working through the terrifying complexity of Einstein's equations. In 1988, they published a groundbreaking paper that shook the world of theoretical physics. Their calculations suggested that a traversable wormhole, one stable enough for matter to pass through without collapsing, might actually be possible. But achieving such a structure required something profoundly strange. The key ingredient emerging from their equations became known as exotic matter. This was not ordinary matter like the atoms forming stars, planets, or human beings. Exotic matter would need to possess negative energy density, something radically different from anything familiar in everyday reality. Ordinary matter creates gravity and pulls surrounding objects inward. Exotic matter, however, would do the opposite. Instead of attracting, it would push outward, resisting the collapse of space-time itself. According to Thorne's calculations, if enough exotic matter could be placed around the narrow throat of a wormhole, its outward pressure could counteract the crushing gravitational forces trying to seal the tunnel shut. In theory, the passage might remain open long enough for a spacecraft to safely cross through it. The scientific community reacted with enormous fascination, not because anyone believed humanity would begin constructing wormholes the following day. No one even knew whether exotic matter truly existed in sufficient quantities, or whether it could ever be controlled. But something far more unsettling had emerged from the mathematics. The equations of general relativity, even in their strictest form, were not forbidding such structures. The laws of nature themselves appeared to leave a door slightly open. And then Thorne realized something even more disturbing. If you can bend space this dramatically, you inevitably bend time along with it. Wormholes might not simply act as shortcuts through space. Under the right conditions, they could potentially connect entirely different moments in time. In other words, a wormhole might someday become more than a bridge between distant galaxies. It could become a doorway between the past and the future themselves. To understand how such a thing could even be possible, let us imagine a small but deeply unsettling thought experiment. Picture a traversable wormhole with two connected openings, two gateways linked by a hidden tunnel through space-time itself. Now imagine keeping one entrance completely stationary while taking the other and accelerating it to enormous speeds, perhaps close to the speed of light, or placing it near an object with extreme gravity, such as a black hole. And this is where Albert Einstein's laws of relativity begin to transform the situation into something extraordinary. Because according to relativity, time slows down for objects moving at extremely high speeds or exposed to intense gravitational fields. Eventually, the two wormhole entrances stop sharing the same present moment. While years pass for the stationary entrance, far less time passes for the moving one, and suddenly, the wormhole no longer connects only two locations in space. It begins connecting two different moments in time. Kip Thorne illustrated this terrifying possibility using a famous thought experiment involving his wife, Carol Lee Thorne. Imagine that Carol Lee places one side of the wormhole aboard a spacecraft and travels deep into space at nearly the speed of light. According to her own clock, the journey lasts only a few hours before she returns. But back on Earth, many years have passed. Because of relativistic time dilation, the moving wormhole entrance has experienced far less time than the stationary one remaining on Earth. And this is where reality becomes truly disturbing. The two ends of the wormhole are still connected internally. Someone standing beside the Earth entrance could look through the tunnel and see Carolee having aged only a few hours. The flow of time on each side is no longer synchronized. If a person stepped through the Earth entrance and crossed the tunnel, they could emerge years in the past relative to Earth's timeline. Someone traveling the opposite direction could leap directly into the future. In that moment, the wormhole stops being merely a shortcut through space. It becomes a theoretical time machine, allowed by the very equations of general relativity itself. And perhaps the most unsettling part is this: none of these ideas come from fantasy alone. They emerge directly from the mathematics describing the structure of the universe. Of course, Kip Thorne presented these ideas with extreme caution. He repeatedly emphasized that humanity was nowhere near capable of engineering such a structure, and that no one even knew whether exotic matter truly existed. But what disturbed him most was not the engineering challenge. It was something far deeper. Thorne began to suspect that the moment a wormhole truly became a functioning time machine, the universe itself might react violently against it. Once the two ends of the tunnel became separated in time, enormous quantum energies could begin building uncontrollably inside the throat of the wormhole. And perhaps nature would respond by destroying the system before it could ever be used. It was almost as if the universe possessed a hidden defense mechanism designed to prevent the past from being altered. Yet despite these concerns, Thorne could never fully prove that such a mechanism must always exist. The mathematics refused to completely forbid time machines. Einstein's equations still left a narrow opening, a tiny crack where the impossible remained theoretically allowed. And it was at that moment that another extraordinary mind entered the debate. Stephen Hawking believed that nature should never permit travel into the past. In his view, the universe had to protect causality itself. If human beings could travel backward and alter events, the logical structure of reality might collapse entirely. Hawking introduced this idea through what became known as the chronology protection conjecture. According to this hypothesis, the universe contains a natural defense system against time travel. Like an invisible cosmic immune system, it would destroy any machine capable of changing the past before it could fully operate. But Hawking did not stop at abstract theory. To explore the idea in his own strange and brilliant way, he designed one of the most unusual experiments in the history of physics. He organized a party. The date was June 28th, 2009. The location was one of the historic halls of the University of Cambridge, and that party would become one of the most unforgettable symbols in the scientific debate over time travel. The room was prepared in perfect detail. Balloons floated gently above the chairs, elegant trays of food rested quietly on the tables, and rows of crystal champagne glasses reflected the soft light across the hall. On one wall, a large banner displayed a strange and unforgettable message: "Welcome, time travelers." Yet despite all the preparations, there was not a single guest in the room. Stephen Hawking sat silently in his wheelchair, his eyes fixed on the doorway as he waited. Minutes passed, then hours, but nothing happened. The door never opened. No visitor from the future appeared. No strange machine emerged from a burst of light, and no footsteps echoed across the floor. The champagne remained untouched, the food slowly cooled, and the balloons drifted silently through the empty hall. But this was not the story of a failed party. It was one of the most imaginative thought experiments ever attempted in modern science. Because Hawking had not sent the invitations before the event, he released them only after the party had already ended. The invitations contained the exact date, time, and even the precise coordinates of the gathering. The logic behind the experiment was beautifully simple. If time travel ever became possible at any point in the future, someone might eventually discover the invitation. And if traveling into the past truly could be achieved, then in theory they could choose to attend Hawking's party. Perhaps a historian living centuries from now. Perhaps a civilization thousands of years in the future. Hawking needed only a single guest. If even one person had stepped through that doorway, it would have become the first direct evidence in human history that time travel to the past might someday be possible. But no one came. Later, Hawking summarized the result with his characteristic dry humor. "I have experimental evidence that time travel is not possible. I waited for a long time, but nobody arrived." And perhaps the most unsettling question begins right there. Was the room empty because no one could come from the future? Or because future civilizations already understood the consequences of interfering with the past and chose never to appear at all? Of course, many clever objections can be raised against Stephen Hawking's famous party experiment. Perhaps the invitations were never discovered in the future. Perhaps time travelers follow strict rules forbidding interference with the past. Or perhaps a time machine can only travel back to the exact moment it was first activated, making a journey to 2009 impossible in the first place. But Hawking's true goal was never to definitively prove that time travel could not exist. The experiment represented something far deeper. Throughout his life, Hawking believed the universe possessed a natural defense mechanism designed to protect the past itself. In his view, reality was constructed in a way that prevented paradoxes from destroying the logical structure of history. Somewhere within the laws of physics, an invisible rule appeared to keep the door to the past permanently locked. In 1992, Hawking transformed this belief into a formal scientific proposal known as the chronology protection conjecture. The core idea was deeply unsettling in its simplicity. If a civilization ever attempted to build a true time machine using a wormhole, like the ones described by Kip Thorne, the universe itself would intervene at the exact moment the machine became operational. As the system approached what physicists call the chronology horizon, ordinary quantum fluctuations would begin spiraling out of control. Normally, tiny energy fluctuations constantly appear and disappear harmlessly throughout empty space. But near a functioning time machine, these fluctuations could accumulate inside the throat of the wormhole, growing larger and larger until the energy density became effectively infinite. The result would be catastrophic. The wormhole would collapse violently before the first traveler could pass through it, or before the first signal could ever be sent into the past. In other words, the machine would destroy itself before history could be altered. Hawking summarized this idea with one of the most famous lines in modern theoretical physics. He suggested that the universe seems to contain a mechanism that prevents the appearance of closed, time-like curves, thereby keeping history safe for historians. In physics, a closed time-like curve is a loop through space-time that would theoretically allow a traveler to return to their own past. What makes this especially disturbing is that Albert Einstein's equations do not completely forbid such structures. In fact, in 1949, mathematician Kurt Gödel proposed a rotating universe model in which these loops could theoretically exist everywhere. Yet Hawking remained convinced that nature would never allow them to form in practice. The chronology protection conjecture was ultimately his way of saying something profound. The universe may contain an invisible immune system designed to protect time itself. Whenever the conditions for a true time machine begin to emerge, reality destabilizes, energy spirals out of control, and the structure destroys itself. In the end, time protects its own history. But there was one serious weakness in Stephen Hawking's idea of chronology protection. Hawking could show that quantum effects might destroy time machines in many possible situations. He could calculate how unstable energy fluctuations might tear wormholes apart before they ever became usable gateways into the past. But he could never prove that this would always happen, under every condition, in every possible universe, for every possible kind of time machine. And so, the chronology protection conjecture remains, even today, not a theorem, but a powerful and unproven scientific intuition. And within that tiny unresolved gap lies one of the most fascinating regions of modern physics. Because the greatest obstacle to traveling into the past is not simply engineering. It is not only that we lack the technology, the exotic matter, or the ability to control wormholes. The deeper problem is that backward time travel appears to create paradoxes capable of tearing logic itself apart. The most famous of these is known as the grandfather paradox. Imagine building a time machine and traveling into the past. Once there, you prevent your grandfather from ever meeting your grandmother. If that happens, your parents are never born. And if your parents are never born, then you are never born either. But if you never existed, you could never have built the time machine in the first place. And if you never built the machine, you could never travel into the past to interfere with your grandfather's life. So your parents are born, you are born, and eventually you build the machine and go back once again. The loop closes in on itself, and logic begins to collapse in silence. This is not merely a playful thought experiment. It represents a direct violation of consistency itself. In physics, events cannot contradict their own existence. The laws of reality must remain coherent. If traveling into the past produces contradictions like this, then either time travel is impossible, or the universe operates according to a stranger logic than the human mind can easily accept. And the grandfather paradox is not the only mystery time creates. Beside it stands another puzzle, just as disturbing and perhaps even stranger. It is known as the self-creating information paradox, and it forces us to face a possibility even more unsettling than changing the past. To truly feel the weight of this paradox, imagine a small scene unfolding in your mind. Suppose you travel into the past and meet the young Ludwig van Beethoven. In your hands are the complete sheet music pages for his future masterpiece, the Ninth Symphony. You give the notes to him. Beethoven studies them in amazement, carefully rewrites them in his own handwriting, and later publishes them as his own compositions. Time passes. The symphony becomes one of the greatest musical achievements in human history. Centuries later, you grow up listening to that same music, and eventually you become the very person who carries those notes back into the past. But this creates a deeply unsettling question. Who actually composed the symphony? Because the music was never truly created by Beethoven, nor was it originally invented by you. The information exists trapped inside a closed loop. It appears to have emerged without any true point of origin at all. Cause and effect fold back onto themselves. And this is not merely a strange philosophical game. What truly terrifies physicists is the way these paradoxes collide with the deepest laws of quantum mechanics. According to modern physics, information cannot simply vanish from the universe. The state of a particle, the outcome of an event, every piece of data woven into reality itself must continue to exist somewhere. Information can transform, spread out, or become scrambled beyond recognition, but it cannot be completely erased from nature's records. This is why the information paradox became one of the greatest problems in modern physics, especially in the study of black holes. If you travel into the past and alter an event, you also alter the information connected to that event. In some scenarios, you may even erase it entirely. And if information can truly disappear, then the deepest structure of quantum mechanics begins to collapse. The mathematical consistency of reality itself starts breaking apart. This is why time travel is not merely an engineering problem. It threatens the logical framework of the universe itself. For decades, paradoxes like the grandfather paradox and the information paradox appeared impossible to resolve. No matter how physicists constructed the scenario, contradiction always returned. Interfering with the past seemed to imply the self-destruction of logic itself, and for that reason, much of the scientific world concluded that the universe must somehow keep the door to the past permanently sealed. For decades, much of the scientific world believed the past was fundamentally untouchable. It was as if the logical structure of the universe itself depended on an invisible wall, preventing history from being altered. But near the end of 2024, a young physicist from Vanderbilt University, Lorenzo Gavassino, published a remarkable paper claiming to resolve this ancient problem. And the solution he proposed was even more unsettling than the paradoxes themselves. Gavassino's approach unified general relativity, quantum mechanics, and thermodynamics within a single framework. But his central idea was deeply disturbing. The universe may not forbid time travel at all. It may only forbid paradoxes, and the method by which it preserves consistency could be stranger than anyone imagined. According to Gavassino, reality might protect the past by targeting the most personal thing you possess, your memory itself. His work approached the grandfather paradox from an entirely different perspective, and he did so without inventing new laws of physics. Instead, he relied only on the laws already known to exist. Imagine traveling inside a spacecraft, moving along a closed loop in time. Eventually, the journey returns you to the exact moment where it began. But here, a terrifying contradiction appears. According to the second law of thermodynamics, entropy, the measure of disorder within a system, must always increase. Hot coffee cools down. Broken glass does not spontaneously reassemble itself. Human beings grow older. The arrow of time itself seems to emerge from this irreversible growth of entropy. Yet inside a closed time loop, this law collides with itself. As the spacecraft moves through the loop, entropy must continue increasing. But once the ship returns to its starting point, the system must also return to exactly the same state it possessed at the beginning. Otherwise, the loop becomes inconsistent. In other words, entropy must somehow both increase and reset itself simultaneously. Disorder must grow, and yet somehow disappear again. This contradiction became one of the deepest dead ends in theoretical physics, and Gavassino's proposed solution was astonishingly dark. According to his model, the universe does not resolve the contradiction by breaking physics. Instead, it resolves it by erasing the traveler's memory. A person moving through a closed time-like loop might not fully preserve the information they experienced during the cycle. Memories could blur, information could disappear, and consciousness itself might be forced to reorganize in order to maintain consistency within the loop. The universe would preserve the past, but possibly at the cost of your identity itself. The most unsettling aspect of Lorenzo Gavassino's work was the idea that the universe does not require any external intervention to resolve these paradoxes. The deepest laws of reality appear capable of silently reorganizing the system before contradiction can ever emerge. Any physical system entering a closed loop in time becomes subject to what Gavassino described as a process of spontaneous decoherence. The technical language sounds complex, but the underlying idea is terrifyingly simple. The geometry of a closed time loop imposes an invisible command on everything trapped inside it. Once the cycle is complete, every component of the system must return to its original state. Not approximately, perfectly. Reality allows no deviation at all. Gavesino explored this using the example of an unstable radioactive particle. Under ordinary conditions, such a particle naturally decays over time. Its structure breaks apart, energy disperses outward, and entropy increases. This is the familiar direction of time itself. Order dissolves into disorder. Systems decay and scatter irreversibly. But as the particle approaches the end of a closed time loop, something extraordinary begins to happen. The decay process reverses itself. The scattered components start reassembling as though guided by an invisible force. The system rebuilds itself. It is as if the film of time has briefly begun running backward. Entropy, which had been increasing throughout the journey, suddenly begins decreasing instead. And when the loop closes completely, the particle returns to its original state, as though nothing had ever happened at all. This is not a violation of quantum mechanics. In fact, Gavesino argued that it emerges directly from one of its deepest consequences. He connected this behavior to a principle long known in statistical physics called Poincaré recurrence. According to this principle, a closed system given enough time will eventually return arbitrarily close to its original configuration. Under normal circumstances, such a return could require timescales longer than the age of the universe itself. But inside a closed time loop, the geometry forces the recurrence to happen within a single cycle. The loop behaves almost like a cage, compelling the system back into its starting condition. The universe preserves consistency by using its own laws against paradox, and this is where the implications begin, moving beyond physics alone, because the same mechanism may apply not only to particles and machines, but to the human mind itself. If everything inside the loop must return to its initial state, then that includes your brain, your memories, your consciousness, and perhaps while protecting the past from contradiction, the universe begins by quietly erasing you. And this is where the truly disturbing implication of Lorenzo Gavesino's work finally emerges, because he applied the same rigid physical logic directly to the human mind itself. According to Gavesino, memory is not merely an abstract thought. Every memory corresponds to real physical changes inside the neural structure of the brain. Every experience, every fear, every face, every sound leaves a measurable imprint within your neurons. Memory is, in a very real sense, a physical object written into matter itself. And if every system trapped inside a closed time loop must return perfectly to its original state, then that law must also apply to your brain. Just as a decayed particle reconstructs itself inside the loop, the neural pathways formed during the journey must also return to their original configuration. The memories created during the loop are erased as though they never existed at all. This is what makes Gavesino's solution both elegant and terrifying. You may enter the time loop. You may complete the journey. You may even attempt to change the past itself. But when the cycle closes and you return to the beginning, every memory of what happened disappears from your mind. The universe quietly resets you before contradiction can emerge. And in this way, the grandfather paradox dissolves without violence or intervention. Information capable of changing the past never survives the loop. The future cannot permanently transfer knowledge backward through time. The laws of quantum mechanics themselves automatically force reality into self-consistency. And Gavesino's idea was actually connected to an older proposal introduced decades earlier by Russian physicist Igor Novikov. During the 1980s, Novikov argued that even if time travel were possible, only self-consistent histories could ever occur. This became known as the self-consistency principle. According to Novikov, the universe does not ban paradoxes by force. Instead, it simply makes contradictory events impossible from the beginning. There is no cosmic police officer intervening to stop you. The laws of physics themselves only allow outcomes that remain logically consistent. Novikov illustrated this idea using a famous thought experiment involving a billiard ball. Imagine a billiard ball entering a time machine and traveling into the past. The ball emerges earlier in time and rolls toward its younger self. If it strikes its earlier version hard enough to completely change its path, then the younger ball would never enter the time machine at all. And if it never enters the machine, it cannot travel back and strike itself in the first place. That is the paradox. But according to Novikov's principle, the universe never allows this contradiction to occur. The collision can happen only in a way that preserves consistency. The ball may slightly alter its trajectory, but ultimately it still follows the path required to enter the machine and complete the loop exactly as history demands. Reality remains internally coherent, and perhaps that is the most unsettling possibility of all. Even if you tried to change the past, you may only end up fulfilling what had already happened all along. The most important detail in Igor Novikov's thought experiment was this: the universe never allows events that create contradiction. The billiard ball cannot strike its younger self with enough force to stop it from entering the time machine. Instead, the collision only slightly alters its trajectory. The tiny deflection changes the path just enough to preserve the loop itself. The ball still enters the machine, still travels into the past, and still lightly collides with its earlier version exactly as history requires. An endless loop, perfectly self-consistent. No logical collapse, no paradox. Lorenzo Gavesino took this idea and grounded it within the rigid framework of quantum mechanics and thermodynamics. He argued that Novikov's principle may not simply be philosophy, but a direct consequence of physical law itself. If closed time-like curves can exist, then the mathematics of the universe may automatically prevent paradoxes from ever forming. Yet one crucial detail remains. Gavesino's work does not prove that such time loops actually exist. Stephen Hawking's chronology protection conjecture may still be correct. The universe might prevent these structures from forming in the first place. What Gavesino showed was something narrower, but deeply unsettling. If such loops can exist, then the physics inside them must remain self-consistent. The universe may bend time, but perhaps it never allows logic itself to break. And at this point, we begin leaving behind the cold laboratories of modern physics and descending into far older layers of human history. Because many of the ideas quantum mechanics is only now beginning to touch seem to have echoed inside ancient myths thousands of years ago. Long before telescopes, atoms, or Einstein, human beings already appeared to suspect that time could flow differently in different realms of existence. One of the oldest and most remarkable examples appears deep within the ancient Indian epic Mahabharata, written more than 2,000 years ago. The story begins with King Kakudmi, ruler of a prosperous kingdom. and his daughter Revati, whose beauty was said to surpass all others. The king becomes obsessed with finding a husband worthy of her, yet no mortal candidate on earth seems sufficient. Finally, he makes an extraordinary decision. Taking his daughter with him, he journeys directly to the realm of the creator god Brahma, known as Brahma Loka. His goal is simple. He wishes to ask the creator himself who should marry his daughter. When they arrive in the divine realm, they find Brahma peacefully listening to a celestial musical performance. Out of respect, the king quietly waits for the music to end. To him, the wait feels brief. Only a few minutes, perhaps no longer than a short melody. But when the performance finishes, Brahma smiles at the king's list of potential husbands, because Kakudmi has failed to realize something terrifying. During those few moments inside Brahma Loka, thousands of years have passed on earth. The men he once considered suitable husbands are long dead. Their children are gone. Their civilizations have collapsed into dust and disappeared into forgotten history. When the king and his daughter finally return to Earth, almost nothing from their old world remains. Everyone they once knew has vanished into time itself. And when we examine this ancient story carefully, its meaning begins to feel strangely familiar. A traveler leaves Earth, enters a higher realm where time flows differently, and returns to find that the outside world has aged dramatically, while they themselves have barely changed at all. It is an astonishing description that closely resembles the very concept of time dilation that Albert Einstein would mathematically describe centuries later. The same physical phenomenon that forces modern engineers to constantly correct the clocks aboard GPS satellites. The strange effect that caused astronaut Scott Kelly to return from space slightly younger than his twin brother on Earth appears in astonishing form within the pages of the ancient epic Mahabharata, more than 2,000 years before Albert Einstein was born. Some historians may dismiss this as coincidence or symbolism, yet the structural similarities are so striking that it becomes difficult not to pause and wonder, because these stories do not merely describe time as mysterious. They specifically portray time flowing at different speeds in different realms of existence. Travelers ascend into higher worlds, and when they return, they discover that entire ages have passed on Earth. And what makes this even more fascinating is that the same idea appears across completely different civilizations. More than 1,000 years later, in 8th century Japan, another story emerges carrying the same unsettling pattern. It is the tragic tale of the fisherman Urashima Taro. The story begins when Taro rescues a small turtle near the shore. In gratitude, the turtle invites him to the magnificent dragon palace beneath the sea. Taro accepts and descends into a magical underwater kingdom. There, he is welcomed by the beautiful Princess Otohime and experiences wonders unlike anything found in the human world. To Taro, only a few days seem to pass. But when he finally chooses to return home, he is confronted with a horrifying truth. His village is gone. His family has died. No one remembers his name, because during the few days he spent beneath the ocean, centuries passed on Earth. The structure of this story closely resembles what modern physics now calls the twin paradox. One observer enters a different reference frame, experiences time more slowly, and returns to discover that the outside world has aged far more rapidly. And this same theme appears again far from the shores of Japan, deep within the deserts of the Middle East. In the story of the companions of the cave found in the Quran, a group of young believers flee persecution and hide inside a cave. There they fall into a deep sleep. When they awaken, they believe only a short period has passed. But upon returning to the outside world, they discover that society itself has transformed. Generations have vanished, religions have changed. The world they once knew no longer exists, because while they slept inside the cave, centuries passed outside. This narrative also mirrors the Christian legend of the 7 sleepers of Ephesus. And what connects all of these ancient stories is something extraordinary. They do not describe time merely as mystical or symbolic. Instead, they portray it almost mechanically, as something capable of flowing differently, depending on location and environment. Travelers cross into isolated realms or higher dimensions where time behaves differently, and when they return, they find themselves permanently separated from the world they once belonged to. Perhaps humanity sensed long ago, long before modern physics existed, that time does not flow equally everywhere in the universe. And now we move toward the cold northern coasts of Ireland, where this ancient intuition takes on an even darker and more tragic form. As we continue tracing these ancient stories of distorted time, our path now turns toward the mist-covered shores of Ireland and the legends of Celtic mythology. One of the most tragic tales tells the story of the warrior poet Oisin and the golden-haired woman Niamh. Niamh comes from Tir na Nog, the legendary land of eternal youth. She invites Oisin to leave the mortal world behind and journey with her across the sea upon a white horse into this mysterious realm. Inside Tir na Nog, time behaves differently. Oisin does not age. The days pass in peace and beauty. There is no suffering, no decay, no death. To him, only a few years seem to pass, but eventually he begins longing for his homeland and the companions he left behind. When he asks to return, Niamh gives him the white horse and warns him with great seriousness. He may visit Ireland again, but he must never dismount or allow his feet to touch mortal soil. When Oisin finally returns, he discovers a horrifying truth. The world he knew is gone. His friends have died, the villages have changed, and everyone he once loved has vanished into history. Because while only a few years passed for him, 300 years passed on Earth. And then tragedy strikes. One day he sees several men struggling to move a heavy stone. Leaning down from the horse to help them, he loses his balance and falls. The moment his feet touch the ground, all the years held back inside Tir na Nog crash into his body at once. Oisin ages within seconds. His hair whitens, his body weakens, and he transforms into an old man before their eyes. This story may be one of the most tragic expressions of time dilation ever imagined, because it is not simply about traveling into the future. It describes the physical cost of leaving a protected frame of reference and returning to ordinary time. Oisin existed outside the normal flow of aging, but the instant he re-entered the mortal world, all the years he escaped returned at once. And what makes this remarkable is how the same structure appears again and again across civilizations. In Indian epics, Japanese folklore, Islamic stories, and Celtic mythology, travelers enter another realm where time flows differently. When they return, they discover the outside world has aged without them. Different cultures, separated by oceans and centuries, repeated the same strange intuition. Time does not move equally everywhere. Perhaps humanity sensed this long before modern science existed. Some ancient texts even described it with surprisingly mathematical precision. In the Buddhist Pali Canon, a single day in heavenly realms is explicitly said to equal centuries on earth. This is not merely poetic symbolism. It is a direct ratio between different rates of time itself. For thousands of years, these stories were carried across generations beside fires and through oral tradition. And then, near the end of the 19th century, everything changed. A young English writer transformed time travel from mystical folklore into a machine. In 1895, H.G. Wells published The Time Machine, a novel that would permanently reshape humanity's imagination. Wells was only a young teacher at the time. He had no laboratory, no prestigious academic position, and no scientific authority. But he possessed an idea powerful enough to influence generations of scientists. Before Wells, fictional time travelers usually drifted passively into other eras through magic, sleep, or divine intervention. No one truly controlled the journey. Wells changed that forever. His protagonist built a machine with his own hands, constructed from brass, crystal, and intricate mechanisms. The device transformed time into something navigable. Time was no longer merely a mysterious river carrying humanity helplessly forward. It became a fourth dimension through which movement itself might be possible. Years before Albert Einstein would mathematically reshape physics, Wells had already planted the idea into human imagination through storytelling. One worked with equations, the other worked with fiction. Yet both seemed to be reaching toward the same hidden truth about the universe. The idea that time might be a fourth dimension was only beginning to emerge within mathematical and scientific circles during the 1890s. But the first person to place this idea into the imagination of the public was not a physicist. It was H.G. Wells. Years later, mathematician Hermann Minkowski would formally describe Albert Einstein's relativity as a four-dimensional space-time geometry. Yet long before Einstein published Special Relativity, Wells had already embedded the same concept into literature. Time was no longer merely an invisible backdrop against which events unfolded. It became something through which movement itself might be possible. During those years, intellectual culture was quietly beginning to abandon the idea of absolute time. Wells transformed that growing intuition into storytelling. Einstein would later transform it into physical law. But the time machine was never just a story about traveling through time. It was also a dark warning about humanity's future. In the novel, the time traveler activates his machine and launches himself more than 800,000 years into the future. At first, he believes he has discovered a peaceful utopia. On the surface live the Eloi, small and beautiful beings who spend their days playing, eating fruit, and living without fear or struggle. Yet beneath this peaceful image lies something horrifying. Deep underground live the Morlocks, pale mechanical creatures who maintain the hidden machinery of the world. Wells transformed the class divisions of the industrial age into a terrifying evolutionary nightmare. The Morlocks are the descendants of the oppressed working class, forced underground for generations inside factories and machines. The Eloi are the weakened descendants of the idle upper class. But over time, the balance of power reversed. At night, the Morlocks emerge from below to hunt the Eloi themselves. Wells fused Darwinian evolution with social anxiety, creating one of the darkest visions of humanity ever written. Yet the novel continues even further into the future. The time traveler pushes his machine millions of years ahead. The sun has swollen into a gigantic red star dominating the sky. The oceans have vanished. The atmosphere has thinned. Silence has spread across the dying earth. Humanity is gone. Only strange crab-like creatures crawl slowly across empty shores beneath the fading light of a dying world. It is one of the most melancholic visions of the future in literary history. Eventually, the time traveler returns to Victorian London, but he cannot remain there. He has seen the true nature of time itself, and at the end of the story, he climbs back into the machine one final time and disappears forever into the darkness of eternity. He never returns. Wells did more than create science fiction. He transformed humanity's relationship with time itself. Wells gave the world the idea that time could be traveled through. Einstein later provided the equations showing how reality itself might allow such things. And when those ideas merged together, time ceased being merely philosophical. It became something physical, something that could bend, stretch, and perhaps someday be crossed. But at that moment, the story begins moving into darker territory. Because once humanity started understanding time, some would inevitably begin trying to control it. The idea of time travel, once confined to imagination and fiction, soon drifted into the dark corridors of military secrecy and wartime paranoia. In October of 1943, inside the shadow docks of Philadelphia Naval Shipyard, the weight of World War II hung heavily in the air. German submarines were devastating Allied ships across the Atlantic, and the United States Navy was desperately searching for a technological breakthrough. If a warship could somehow become invisible to radar, magnetic mines, or even the human eye itself, the balance of the war might change forever. Out of this mixture of fear, desperation, and ambition emerged one of the most disturbing legends in American history. The story known today as the Philadelphia Experiment. At the center of the legend stood the USS Eldridge. Officially, it was an ordinary destroyer escort vessel, but according to the rumors, it had been selected for something far more dangerous. Under a classified operation allegedly called the Rainbow Project, the ship was surrounded by massive electromagnetic generators. Some versions of the story claimed the experiment drew inspiration from Albert Einstein's unfinished unified field theory. The objective was extraordinary. By bending the structure of space around the ship, scientists supposedly hoped to divert light and radar waves around it, rendering the vessel invisible. As the generators powered up, witnesses described a strange green mist forming around the hull. The electromagnetic field intensified, the haze thickened, and then, according to the legend, the impossible happened. The USS Eldridge vanished, not merely from radar screens, but physically disappeared from sight itself. Later accounts claimed the ship briefly materialized nearly 300 kilometers away, near the Norfolk Naval Shipyard, before disappearing again and returning to Philadelphia. But the true horror supposedly began after the ship came back. The scene described by later storytellers sounded less like a scientific triumph and more like a nightmare. Some crew members were allegedly found fused into the metal structure of the ship itself, as if flesh and steel had been forced to occupy the same physical space. Others survived with severe burns. Some reportedly lost their sanity completely, and a few sailors were said to have vanished forever, swallowed somewhere inside the distortion of space and time. For decades, the United States Navy categorically denied the entire story. Official records indicated that the USS Eldridge was not even in Philadelphia during the dates in question. The primary source behind the legend, a man named Carl Meredith Allen, also known as Carlos Allende, gave contradictory and inconsistent accounts. From the perspective of modern physics, the claims appear extraordinarily implausible. No known electromagnetic field could make an entire warship vanish or teleport through space, and Einstein's unified field theory was never completed. Yet despite all this, the Philadelphia experiment refused to disappear from public imagination. Because the story was never truly about a ship, it was about humanity's desire to control reality itself. And perhaps the most unsettling possibility hidden beneath the legend was this: if space can truly bend, could time fracture with it? The reason the Philadelphia experiment survived for decades was not simply because the story sounded terrifying. What truly unsettled people was the very real military atmosphere surrounding that era. During World War II and the years that followed, the United States military genuinely conducted experimental research involving electromagnetic systems, radar technology, and psychological manipulation. In times of war, governments become willing to push against the known limits of science. And sometimes, the real projects later uncovered appear even stranger than conspiracy theories themselves. For example, MK Ultra was once dismissed as paranoid fantasy. Yet decades later, declassified documents revealed that the CIA had indeed performed mind control and behavioral experiments on human subjects. Likewise, Operation Paperclip confirmed that hundreds of German scientists were secretly brought to the United States after the war. Because of discoveries like these, stories such as the Philadelphia experiment never fully disappeared from public imagination. People began asking a disturbing question: if those projects were real, what else remained hidden? That question leads us to another lonely place on the eastern edge of America, standing above the Atlantic cliffs beneath the shadow of a giant radar tower. Camp Hero State Park. Today it appears peaceful, a quiet coastal park where tourists walk along the grass, while ocean winds sweep across abandoned concrete structures. But during the Cold War, Camp Hero served as a military radar installation designed to detect Soviet bombers approaching the American coastline. Even now, the enormous radar tower still rises above the cliffs, like the skeleton of some forgotten machine. Bunkers, underground tunnels, and decaying military buildings remain scattered across the landscape. Officially, the base was closed in 1969, yet the rumors only began growing after that. According to some accounts, although the surface property was transferred to the state, underground sections allegedly remained under federal control. That small detail fueled decades of speculation about hidden laboratories buried beneath the site. Locals spoke of strange humming noises beneath the earth, compasses behaving erratically, and unexplained lights appearing at night. Then, during the 1990s, the book, The Montauk Project, Experiments in Time, pushed the legend into even darker territory. Its author, Preston Nichols, claimed that Camp Hero had been used not merely for radar research, but for experiments involving consciousness manipulation, psychic phenomena, and even time travel itself. According to the story, a mysterious device called the Montauk chair could allegedly transform human thoughts into physical reality. Some versions even claimed the system could open portals through space and time. More bizarre still were the stories suggesting that sailors lost during the Philadelphia experiment had somehow emerged decades later inside the Montauk facility in 1983. Of course, none of these claims are supported by reliable scientific evidence. Modern physics offers no support for such phenomena, and no verified documents or laboratory data have ever confirmed the stories. Yet despite this, the Montauk legend deeply influenced modern culture, because these stories were never only about time travel. They reflected a darker fear, the possibility that human consciousness, reality itself, and government power might somehow collide in secret. And perhaps the strangest part was this: people did not merely want to believe these stories, they wanted to fear them. The fact that Stranger Things was originally developed under the title Montauk was no coincidence. The show's secret experiments, psychic abilities, and portals into other dimensions were directly inspired by the legends surrounding Camp Hero State Park. Rusted radar towers, abandoned bunkers, and rumors of hidden underground experiments became part of modern mythology. The Montauk Project was almost certainly fictional, yet the reason the story survived for so many decades lies in something deeper. People have long suspected that governments and military organizations might push the boundaries of physics behind closed doors, because the unknown is frightening, and the human mind instinctively fills empty spaces with stories. But the irony is this: real-time machines are not hidden inside underground bunkers or conspiracy theories. They are operating openly in front of the entire world, and they are far more extraordinary than fiction. Today, the most powerful time machine on Earth exists inside CERN, within the gigantic particle accelerator known as the Large Hadron Collider. Buried roughly 100 meters beneath the border between Switzerland and France, this 27-kilometer circular tunnel is one of the largest scientific machines humanity has ever built. Inside it, protons and other subatomic particles are accelerated to speeds unimaginably close to the speed of light, nearly 99.999999% of light speed itself. And at that moment, Albert Einstein's equations begin to dominate reality. According to special relativity, as an object approaches the speed of light, time for that object slows relative to the outside world. This is no longer theoretical speculation. It is measured and confirmed inside laboratories every single day. The particles racing through the collider experience time more slowly than we do. Some particles that should vanish almost instantly survive far longer than expected, simply because time itself has slowed for them. In other words, these particles are physically traveling into the future, not metaphorically, not symbolically, but measurably, mathematically, and experimentally. And perhaps that is the most astonishing part of this entire story. Humanity once tried to explain the mystery of time through myths, gods, caves, and legends. Today we observe those same truths unfolding inside machines built by human hands. Time can bend, it can slow, and it can flow differently for different observers. It is no longer mythology. It is one of the deepest laws of the universe itself. One of the clearest pieces of evidence for time dilation comes from subatomic particles known as muons. Muons are unstable particles created when high-energy cosmic rays collide with atoms high in Earth's atmosphere. Under normal conditions, a muon survives for only about 2.2 microseconds, that is less than a millionth of a second, before it decays and disappears. With such a short lifespan, even moving near the speed of light, a muon should theoretically travel only a few hundred meters before vanishing. Yet something extraordinary happens. These particles are regularly detected at the surface of Earth, despite being created nearly 10 kilometers above it in the atmosphere. Somehow, they survive far longer than expected and reach the ground. There is only one explanation: time dilation. Muons move so close to the speed of light that time for them slows dramatically relative to us. From the muon's own perspective, its lifetime is still only 2.2 microseconds. But from our frame of reference on Earth, its internal clock appears slowed down. As a result, the particle survives long enough to travel much farther than classical physics would allow. In other words, Albert Einstein's predictions are not abstract mathematics. They are silently confirmed every moment inside Earth's atmosphere. Laboratories such as CERN repeatedly observe the same effect in particle accelerators. Forward time travel is no longer science fiction. It is an ordinary consequence of relativity. But all of this leads to a far deeper question. If time can bend forward, could it ever reverse? This is where one of the strangest structures in modern physics appears. In 1963, mathematician Roy Kerr solved Einstein's field equations for rotating black holes and discovered something unexpected. A non-rotating black hole compresses everything into a single point, but a rotating black hole forms a ring-shaped singularity instead. Mathematically, some solutions suggested that a traveler passing through this ring might avoid destruction and emerge somewhere else entirely. Perhaps another region of space. Perhaps another point in time. Under such extreme gravity, the distinction between space and time begins to blur. Motion through space may theoretically become motion through time itself. Of course, building or controlling such structures remains far beyond humanity's capabilities. Yet the equations of physics still refuse to completely close the door on the possibility. And then, in recent years, ideas that once seemed purely theoretical began appearing again inside astonishingly small experiments. In 2025, physicist Philippe Walter and his team at the University of Vienna performed an extraordinary experiment. They did not attempt to bend space-time with giant machines. They did not create wormholes or black holes. Instead, they pursued something smaller, but equally unsettling. They attempted to reverse time for a single photon. Using highly controlled lasers, special crystals, and quantum optical systems, the team manipulated the quantum state of a photon and then attempted to reverse the process itself. In classical physics, reversing an event would require complete knowledge of every detail of the system. But quantum mechanics behaves in far stranger ways. At the quantum level, nature sometimes allows processes that appear astonishingly close to reversing the flow of time itself. And this forces us to confront an uncomfortable possibility. Perhaps time is not as rigid as we imagine. Perhaps at the smallest scales of reality, the boundary between past and future is far less absolute than it seems. At the most critical stage of the experiment, the researchers managed to reverse the photon's journey through the crystal using the principle of quantum superposition. But the strangest part was this: they restored the particle to its original state without directly measuring what had happened to it along the way. In other words, they reverse the process without collapsing the quantum state itself. Philip Walter and his team compared the process to having a remote control for time. In a movie theater, the film only moves forward. But at home, with a remote in your hand, you can press rewind and return to any scene you want. In the quantum world, something disturbingly similar appeared to happen. The photon returned perfectly to its initial state, as if every event it had experienced had simply been erased. The experiment achieved an accuracy above 95%, far too precise to dismiss as coincidence or statistical noise. At microscopic scales, the laws of nature seem to allow time itself to reverse. The one-directional arrow of time we experience in everyday life may not be a fundamental rule of the universe after all. It may only be a statistical tendency emerging from large systems, a broken egg, a cooling cup of coffee, the aging of the human body. These are rules of the macroscopic world. But at the quantum level, nature sometimes behaves differently. Time does not always appear forced to move in only one direction. These extraordinary laboratory results lead directly into one of the most unsettling ideas in modern physics, the concept known as the block universe. According to this model, time is not a river flowing from past to future, the way we experience it. Past, present, and future all exist simultaneously. The universe is not merely a three-dimensional stage. It is a four-dimensional structure in which time itself is woven into reality. In this view, the past never truly disappears. The future is not an unwritten void waiting to happen. Everything already exists at once, like every page of a finished book, printed and bound together. We are simply conscious observers reading those pages one by one. That is why we experience the illusion of time flowing. But the first page and the final page already exist simultaneously. The moment you were born, the second you are hearing these words now, and the final moment of your life, all of them remain permanently embedded somewhere within the fabric of space-time. Time may not be moving at all. Perhaps we are the ones moving through it. Our consciousness can only experience a narrow slice of this vast structure, which is why we remember the past but cannot see the future. That limitation may simply come from the thermodynamic laws governing the human brain. Yet from the universe's own perspective, yesterday and tomorrow may be just as real as this present moment. And some modern physicists push the idea even further towards something deeply unsettling. Perhaps time is not a fundamental feature of reality at all. Perhaps it is only an illusion emerging from the deeper structure of quantum entanglement itself. And if that is true, then the unstoppable flow we have felt our entire lives may be nothing more than the way our minds organize reality around us. The deeper we look into the strange nature of reality, the more our emotional connection to time begins to change. As the rigid boundaries we once believed in slowly dissolve, what remains is the quiet and almost sacred silence of existence itself. Perhaps this journey was never only about physics or laboratory experiments. Perhaps it was also about the human need to understand our place inside the flow of time. Tonight, we watched atoms vibrate across negative intervals of time. We saw clocks betray one another through the effects of time dilation aboard airplanes and satellites. We listened to ancient stories of kings returning to worlds that had aged without them. We imagined the silent champagne party where Stephen Hawking waited for time travelers who never arrived. And beyond all the equations, theories, and experiments, perhaps one truth quietly remained. Humanity has never only tried to understand time. We have always been trying to make peace with it. Because the greatest mystery of time is not physical, it is emotional. Moments matter because they end. Certain nights feel heavy because we know they cannot last forever. Love carries weight because it is temporary. The fragility of life is exactly what gives it meaning. If nothing could ever truly be lost, then nothing would ever feel precious. Perhaps the forward movement of time is not a curse at all, but the invisible force that gives depth to existence itself. Albert Einstein once wrote that the distinction between past, present, and future may be only a stubborn illusion. And perhaps he was right. Maybe somewhere inside the vast four-dimensional structure of the universe, your childhood still exists. Maybe the face of someone you once loved, the night you first felt fear, or the moment that changed your life forever is still there, quietly embedded within space-time itself. Perhaps nothing is ever truly erased. Perhaps those moments simply remain beyond the coordinates our minds can reach. But human consciousness cannot perceive the entire structure at once. We only experience the flow, and whether that flow is a fundamental law of physics or a magnificent illusion created by the mind, it gives birth to the purest emotions we possess: longing, love, fear, hope, memory. All of them emerge from time itself, and maybe the greatest mystery of the universe is not how to travel into the past, but why passing moments feel so deeply human. And now, as the silence of the night slowly surrounds you, perhaps for the first time, it is enough not to stop time, but simply to feel it passing by. And now, as the universe slowly fades back into silence, perhaps the most extraordinary discovery is not that time can bend, slow, or even seem to reverse. Perhaps it is the realization that every fleeting moment of our lives carries weight, precisely because it cannot be held forever. Somewhere beyond the reach of our senses, the stars continue their endless motion. Ancient photons drift silently through the dark, and the fabric of space-time keeps unfolding in ways we are only beginning to understand. Yet here, in the quiet rhythm of a single human life, time still feels deeply personal. It lives inside memories, fading voices, unfinished conversations, and the soft ache of moments we wish had lasted longer. Maybe the universe was never asking us to conquer time at all. Maybe it was only asking us to notice it, to feel the beauty hidden inside passing moments. And as the night grows heavier around you and your thoughts slowly begin to drift, remember this: every second you have ever lived still belongs to the universe. Nothing is ever truly lost. It simply moves beyond the horizon of what we can see.